Okay, for this example, we are going to examine a container of ice cream which weighs 9 pounds, and we're supposed to determine this force P required to produce some type of motion of the container and determine if that motion is either sliding or tipping. So this is a really good example of looking at alternatives of what we might have, because we have multiple different types of motion. If we kind of look in on this bucket again, we need to see if we are going to have some type of sliding motion on here, or if the force is such and the weight is such that we have tipping. Notice if we have tipping, where it tips about, right? That force that I'm showing here that's drawn there, that really is always horizontal type force. It doesn't stay perpendicular if it is tipping. Okay, but we either have this type of sliding or we have this type of force. Okay, so I've drawn the free body diagram, and the first thing I want to do is analyze for tipping. I'm going to look at what my case is for tipping. And you saw when that bucket started to tip, where did it want to tip? It wanted to tip around this corner. So this is where our normal force will be. All right, so this is our normal force, and we have our friction force, which is trying to oppose any motion. So this is our friction force, F. We can use this free body diagram then to solve for our frictional force that we will see here, or our force P that we will see. What we can do is we can easily solve for this. We're looking for P, and in this case, if we look at this point, we'll call it A, we can sum moments about point A. Set that equal to 0 and solve for P. And we will see that we get P is equal to 3.9 pounds for tipping. Okay, so that's key for us. That's one analysis. Now we need to repeat this and look at sliding. Okay, so for this case on sliding, we have our free body diagram shown here. I need to add to this free body diagram my normal force and my frictional force. We don't know where that location is for this normal force. I'm just going to pick some random location here for a normal force. And then again, my frictional force opposing the motion, right? P wants to push it to the left. My frictional force will want to resist that motion and put it to the right. But we don't know exactly where that normal force is. And the reason we don't is we have some odd, who knows what, distribution of force for normal because of our tipping that we're possibly seeing, right? You know, as you're pushing more with this P in this direction, this thing wants to eventually tip. So this side, the right side, may have less normal force than the left side would have. Okay, so how do we solve problems like this for sliding? We know that if it is just about to slide, right? If we know that our force F, for our frictional force, is just impending motion, right? We know then that we have F is equal to mu n. We know our static coefficient of friction. We don't know our normal force. We can solve for our normal force. We can solve for our normal force by just summing forces in the y direction equals 0. We have, of course, we have our 9 pounds negative plus our normal force. N is equal to 9 pounds. We can now use that value, substitute it in for our frictional force, and solve for our frictional force. We have Fs equals 0.6 times our 9 pounds. Fs is then equal to 5.4 pounds. Now we can sum forces in the x direction. we have a positive 5.4 pounds minus our P force that we have up there on our free body diagram. So P equals 5.4 pounds. So now the question is, do we have sliding or tipping? We see our tipping force was 3.9 pounds and our sliding is 5.4 pounds. So if we look at our graph again, we have our graph here. This is our force F or P that we're applying, and this is the distance that the ice cream is moving. If you remember in that, we had this where the force would continue up, and then at some point it would hit our impending motion and start sliding. This force here is our impending motion one, that is 5.4 pounds, and our tipping is at 3.9 pounds. So we see that we will have tipping, right? Tipping is going to occur before the 5.4 pounds, so our answer in this case is that this bucket is going to tip. Okay. Let's take this problem one step further and let's analyze where we're at the point of, if I redesigned this bucket, where would this be such that it might tip or slide first, right? Where is this 5.4? How wide do I need to make that bucket? So let's draw a new free body diagram. Okay, so here's the free body diagram for the situation where we don't know where this normal force is. We want to find out what that distance x is from the center of the pail, such that it may tip or slide, right? It's on the verge of impending motion. Anything more than x, it will definitely slide, whatever value we get for that. Anything less than this value that we get, it will want to tip. So let's take a look at this. Again, if we're at that situation, then we know that our F is equal to mu n. We solved before that n was equal to our, oops, this is supposed to be 9 pounds, right? Is equal to 9 pounds when we summed forces in our y direction. We solve for F of S to be equal to 5.4 pounds. So how do we find X? We simply find that by taking moments at A. So let's take moments at A, and we would get an equation that looks like this. But we know P also, right? If it is impending motion. If we know that P is equal to F, which is equal to our 5.4 pounds. So we can plug that back in and then solve for x, and we will find that x is equal to 4.8 inches. What that is telling us is, in order for this bucket to slide, we would have to increase this from here to here and redesign a new bucket to have this distance be 4.8 inches, and then it will slide as opposed to tipping. Okay? If you have any questions, please let me know.